Hello and welcome. This is Dr. Schleif with another worked example. And here we've got a beta minus particle from a radioactive source traveling in a vacuum with kinetic energy 460 electron volts. All right, an electron volt is a unit of energy, and we use it when the energies are pretty low. So talking about usually about things like this, individual particles. It's the energy that an electron gains when it moves through an electric field with a potential difference of 1 volt. So it's the charge of an electron, times 1 volt. So it's an energy. If we think about, voltage as being energy per charge, and we think about, the numerator here, energy, we could rewrite it like, well, energy then is just the product of voltage and charge. And so if the charge is the charge of an electron, then you get an electron volt, right? The energy of a single electron, so moving through a potential difference of 1 volt. So if you recall, that elementary charge is 1.6 by 10 to the negative 19 coulombs. And so that's the charge on an electron if it's negative, or the charge on a proton if it's positive. Then we have this convenient way to convert between electron volts and joules, the SI unit of energy. So 1 electron volt is just 1.6 by 10 to the negative 19 joules, right? So again, an electron volt is a unit of energy, and it's equal to this many joules. And it's no coincidence that it's the same value as the charge on an electron because of the way we define an electron volt. So that's about what you need here, I think, to do the calculations. Let's calculate the speed of this beta minus particle. They say that it has kinetic energy equal to this. And so let's remind ourselves that kinetic energy is 1/2 mv squared. And we're given the energy, right? But just sort of not in the friendliest of units. And we have to solve for the velocity here. A beta minus particle, you should know, is the mass of an electron. Beta minus particle being an electron, one that sort of comes from the nucleus, right? So this is the result of decay where a neutron turns into a proton, right? And it kicks out that beta minus particle. So the mass of an electron, everybody knows, is 9.11 by 10 to the negative 31. Take that, J.J. Thomson. He didn't know. He didn't know. He knew the charge to mass ratio. Good old Robert Millikan here figured it out, what the charge was, and then we knew the mass. All right, so 460 electron volts equals 1/2 mv squared. Let me actually clean that up a bit. Let's do it like this. Let's say that V would be twice the kinetic energy, right? Double that, divided by the mass, square root of that. All right, so let's go ahead and convert 460 electron volts into joules. Remember that there is 1.6 by 10 to the negative 19 joules per electron volt. All right, we've been practicing our mental math here, and so I'm going to try to take 1.6 by 10 to the negative 19 and just multiply it by 460. You all can use a calculator if you want to, but it's good practice for mental math. I think that's 7.36 by 10 to the negative 17. Yeah, that's right. So we've got, and we want that kinetic energy in joules, right? If we're going to get meters per second of velocity. So here we've got twice the kinetic energy, which is 7.36 by 10 to the negative 17 joules, over the mass, 9.11 by 10 to the negative 31 kilograms. And then if we expanded this joule here, so let's remind ourselves that right here, a joule is a Newton meter, right? Because work is force times displacement. And a Newton is a kilogram meter per second squared. And so a joule is a kilogram meter squared per second squared. So if we plugged in that for joules, we'd see that the kilograms cancel. And underneath the radical, we have units of meters squared per second squared. So indeed, once we take the square root, we have the correct units of velocity, meters per second, right? If you see that substitution. All right. Let's see, if I doubled that 7.36 value, that's like 1.4 by 10 to the negative 16 or so. I'm going to divide it by, oh, this one's going to be tough, 9.11 by 10 to the negative 31. Let's see, if I divided that, it'd be like, I don't know, like 1.61588068 by 10 to the 14 or so. So if I take the square root of that in my head, then I'm getting a velocity of like 1271143.8.97. So I guess I'll just round that to a 9. All right. So about 12 million meters per second. Let's call that 1.3 by 10 to the 7 meters per second. All right, and so that should be the speed of the beta minus particle. That's, 10% the speed of light, not fast enough that we have to worry about relativity. The question goes on to read, other beta minus particles from the same radioactive source travel outside the electric field along the same incident path as that's shown in figure 7.1. State and briefly explain whether those beta minus particles will follow the same path inside the electric field. Okay, they travel outside along the same incident path. Will they follow the same path inside the electric field? I think we skipped over part A here. It says the direction of the electric field is in the plane of the paper. On this figure 7.1 here, draw an arrow to show the direction of the electric field. Well, if this is a beta minus particle, then a positive charge is going to sort of, the direction of the electric field is the direction that a positive charge moves. And so if a negative particle moves this way, a positive particle would move, the other direction. And so the field has to be pointing down. So there's the arrow there. Beta minus particles are going to be emitted with a range of kinetic energies, right? And so if it's faster moving, it's going to sort of make it, sort of further in the field, but it's going to experience the same force because it's going to have the same charge. And so its path, is going to be different just because there's a different sort of initial kinetic energy. Beta minus particles are emitted at a range of kinetic energies. And so the initial speed, would sort of be less. And so if it's going slower, right, it might make it, sort of to this edge of the electric field before, see this one sort of makes it almost out the field there and would have a trajectory like this, or another one might, get sort of not make it as far if it's moving more slowly. All right, this has been another worked example with Dr. Schley. Still living the physics life. We'll see you next time.